Welcome back to our course on scanning electron ion probe microscopy in material characterization. Today, we will begin another part of this course, that is scanning probe microscopy. In this lecture, I will introduce you about the scanning probe microscopy, the basic, the brief history, what is a scanning probe microscope, properties of the scanning probe microscope and different types of scanning probe microscope. So far, we have covered two different type of scanning microscopy, scanning electron microscopy and scanning ion microscopy. Scanning electron microscope has been extensively used for last around 60-70 years, and scanning ion microscope has recently been introduced. And both these microscopes, scanning electron microscope and scanning ion microscope, provides us three-dimensional image of a surface of any sample, solid sample, to a resolution better than 1 nanometer. And in these two microscope, first let us say scanning electron microscope, we use electron beam as a probe. So, electron beam scans on the surface of the specimen, and the signal generated is used to create three-dimensional image. And one of the demerits of the scanning electron microscopy is the diffraction, because electrons have very small mass, and in the electron microscope we have several aperture lenses. They undergo diffraction, and that limits the resolution of scanning electron microscope. Moreover, the electron wavelength is much smaller, therefore, the resolution is much higher or better than optical microscope. Using an electron microscope, our wavelength can be in the range of 0.01 or less, 0.01 nanometer or less. Therefore, we could achieve the resolution less than 1 nanometer using scanning electron microscope. And then if we go to ion microscope, particularly we have talked about helium ion microscope, where helium ions are used as a probe for the microscopy purpose. And because helium ions have a heavier mass, therefore, its wavelength is much smaller. The wavelength of helium ion microscope or helium ions in a helium ion microscope is around 86 times smaller than that of electrons. Because of smaller wavelength, we can get better resolution. We know resolution is proportional to the wavelength, directly proportional to the wavelength. So, by having a smaller wavelength, we could have a better resolution, that means smaller R value. So, smaller distance between two objects can be measured using an ion microscope. And then again helium ions, because it is heavier than electrons, it cannot penetrate much deeper into this specimen. Therefore, the signals are generated near the surface of the specimen or sample, thereby giving resolution much better than scanning electron microscope. In both these cases, scanning electron microscope and scanning ion microscope, we normally use high vacuum through which electron beam passes or ion beam passes to interact with the specimen. So, and then if we talk about the final one, in the first one electrons is used as a probe, and the second one ion is used as a probe, and in the third microscopy again it is scanning probe microscopy. Here the probe is a physical probe rather than any other things. It is a physical probe, means it is nothing but a metal tip directly it touches or almost touches to the specimen, and it interacts with the specimen, and their interaction can give us also a three-dimensional image. So, it is nothing but like a blind man stick. a blind man uses his stick to know the surface or to know the rod and positions of different objects. Similarly, here a finer or smaller probe is used, like in using our finger we can touch an object and know its shape and size, whether it is smooth or rough. Similarly, by using a very fine probe, very small size probe, we can get the information in that range. If my probe is of size of 1 millimeter, then I can get information in the 1 millimeter range. If my physical probe is of size 1 nanometer, then I can get information in the 1 nanometer range. So, using atomically sharp tip, a probe with atomically sharp tip, we can get information of at the atomic level using this scanning probe microscopy. In all these three cases, first case is electron beam scan as a raster, second case ion beam scan across a raster as a raster and provides the information. Similarly, in the third cases, a physical probe scan across the surface and gives us signal, providing us the information that can be used to create three-dimensional image. So, in these third cases, we actually do not need vacuum, that we will see later why we do not need vacuum. In the previous cases, because electron will scatter if we do not have vacuum. Electron cannot pass a millimeter, something like that, at open environment. So, we need to evacuate its way so that electron beam pass through the way to interact with the specimen. But in a physical probe, like my pen is touching the screen, in the same way a physical probe can touch any specimen, almost touch a specimen, and then therefore, we do not need vacuum in the scanning probe microscopy. If we go for definition, then the microscopy that produces images of surface by mechanically scanning or moving a physical probe on the specimen line by line and recording the probe surface interaction as a function of position is nothing but scanning probe microscopy. And it was known to us with the invention of scanning tunneling microscope in 1981. But if we look at the history, the discovery credit should goes to Russell Young in 1971 for his discovery on a technique that is called that is we say topographiner, which was used to know the smoothness or roughness of the surface. As it is written here, the how flat a crystal surface, it was an article by Russell Young, how flat a cleaved surface. Some instrument would able to provide it, and there was a technique called topographiner, which was developed by Russell D. Young in 1971, and he could achieve the roughness of the surface in the range of few nanometer, 2 to 3 nanometer, the depth resolution and the horizontal or lateral resolution about 400 nanometer using the topographiner. Subsequently, in 1981, the first scanning tunneling microscope was constructed by Binning, Rohr, Weibull and Gruber. If we see the components used for scanning tunneling microscope, all the components were available since long back. Though it was discovered in 1981, the components used in the scanning tunneling microscope had been available from 1930s, 1920s. So, it is very simple, the design is very simple, all components were available, but its discovery was quite later in the history, that is in 1981. That is one of the amazing things that there are several things available to the scientific community, but sometimes they are not efficiently or properly utilized to get the information. So, in 1982, using their scanning tunneling microscope, they could obtain the image of a silicon 111 surface, where they could see the atoms, as you see here how the atoms are arranged on a silicon 111 surface. All these white dots that you see, those are atoms. So, you see how clearly and distinctly the position of the atoms are visible in a scanning tunneling microscope image. So, using a simple probe scanning over the surface, they could achieve to get the image which is much better than atomic resolution in the Armstrong range. That is what they achieved in 1982, and for their contribution they received Nobel Prize in 1986. These two scientists, Gerd Binning and Heinrich Rohr, received the Nobel Prize in 1986 in physics. One half of the Nobel Prize was given to these two scientists for their discovery of scanning tunneling microscope. Another half was given to the Ernest Rosca, who was credited for his contribution on the electron optics, particularly for the design of electron microscope. The another scientist we have seen who had contributed extensively for the ion microscopy is the Erwin Muller, who died in 1977. Therefore, probably he could not receive the Nobel Prize, otherwise he was another contender of Nobel Prize for his contributions on the development of ion microscope. That Ernest Rosca and Erwin Muller both were working at technical universities of Germany, Berlin, together in the same university. One was working on the electron microscopy, another was working on the electron emission or field ion microscope. Later stage that become the main topics of his research, and he has presented the atomic level resolution of samples of some of the metal using the field ion microscope. So, what is actually a scanning probe microscope? Here certainly a physical probe is used, as we talked. A physical probe or tip is scanned over a surface to get an usable signal to create an image. So, now here is a physical probe or tip, and the tip shape and size is quite important here to get the information of the specimen. In order to achieve atomic resolution, the tip should be atomically sharp. There should be only single atom at the apex of the tip, and that will go and scan over the surface, very close to the surface, in the gap less than 1 nanometer between the sample and tip, and it will scan and a signal generated. In this particular cases, the signal can be current, that can be tunneling current, that can be force. The signal can be anything depending upon the sample we are investigating and what type of signal we would like to measure. And in these cases, there is no lens. Like in electron microscope, ion microscope, we have seen that we use condenser lens, we use objective lens, and we use reflectors for scanning the electron beam or ion beam across the surface. But here no such lens are used, just directly a physical probe is being scanned over the specimen. So, therefore, only a probe is there, and you should have a scanning unit and a feedback controller that would allow you to scan across the surface in a controlled manner. Therefore, that is a feedback controller, and quite simple in design, as you see here. The information signal detected, the information or detected signal depends on the several factors such as tip of the physical probe, specimen platform stability, sensitivity of the device. These factors significantly play a significant role in getting the information from the surface. Like if the tip is very close to the specimen, and if you apply, as you see here, if you apply a bias, then current will pass between the sample and tip. If the tip is more closer to the specimen, more current will pass. If the tip is more little away from the specimen, less current will pass. Similarly, for example, if my sample is magnetic in nature and my tip is magnetic in nature, the magnetic field magnetic field can extend up to certain distance above the surface, and we do not need to come very close to this specimen to experience the magnetic field. The tip can scan little above the specimen and know which place a magnetic particle is present, and the magnetic by experiencing the magnetic field on the specimen. So, this is called magnetic force microscopy. There can be different type of force, van der Waals force, magnetic force, chemical force, all these kind of force can be also measured between the tip and the specimen to get the information such as magnetic properties, chemical properties, electrostatic properties. Such kind of information of the surface can be obtained. Here do we need the vacuum? So, here actually we do not need vacuum theoretically, but if we want to get information of the surface, very surface or in the atomic layer, actually in practical you will see later that we also need high vacuum. Theoretically or practically we do not need vacuum at all. Without vacuum we certainly can do it and get information, but if we without vacuum, in the normal atmosphere we have many gas molecule, and this gas molecule will adsorb on the surface of a specimen, and as we are going to see or study the very surface of the material, we actually may not study the very surface of the material, but rather the gases of our environment which is adsorbed on the specimen that we will study. So, therefore, if we want to study the exact properties of the surface has to be very clean, nothing should be adsorbed on the surface, then only we can see the material surface or the atoms of that material on the surface. Otherwise, just for the morphology we do not need vacuum. The properties of the scanning probe microscope, these are used to obtain surface topology of relatively flat sample. When I say relatively flat sample, certainly it has to be flatter than that we study in the scanning electron microscope or helium ion microscope. If it is not very flat enough, then there is more probability or chance that tip will touch the specimen and its tip surface will be damaged. As you will see that it is atomically sharp tip. If we are scanning, if the surface is very up and down, there is more probability that tip can touch the surface of the specimen and thereby getting damaged, and then we cannot get the accurate information from a damaged tip. So, we expect relatively flat sample. There are other reasons why we need relatively flat sample. It is not our scanner unit or the tip with the scanning unit which allow the tip to scan, they cannot move very fast up and down and left and right to as they cannot move very up and down very fast or left and right x to y direction very fast. Therefore, we cannot do very rough sample, and the reason of that these physical probe cannot move very up and down is that the piezoelectric sensor that we use, they have their limitations. First thing. Second thing is that we are going to measure here the information at the atomic level. So, therefore, the sensitivity has to be very high. So, in that type of sensitivity, if by doing a very finer control, we cannot do both rough control and finer control simultaneously. Either we can do the rough control of the rough moments or the finer moments. So, thereby not allowing us to measure very rough sample using this technique. SPM can also measure local properties such as friction and magnetic properties, and this is what that also can be done because that probe is moving slowly across the surface, therefore, it can measure frictional properties of the specimen. The thickness of monoatomic layer can be measured very precisely. Here monoatomic layer means on the surface, if on a surface if on the specimen there is a single layer of single monoatomic layer present, then the tip will go slowly above it and then find a monoatomic layer, and when it find a monoatomic layer, it will go a little up and giving the thickness of the monoatomic layer. Monoatomic means one atom, and our one atom at the tip is going and scanning will allow us to provide the thickness of the monoatomic layer, exact thickness of the monoatomic layer, or it is diatomic layer or triatomic layer, like all graphenes, whether it is single layer graphene, double layer graphene, triple layer graphene, all these thickness can be measured very precisely, accurately using this technique. The mechanical and electrical properties can be measured at the atomic scale by positioning the tip with respect to sample. Different type of mechanical and electrical properties can be measured using this technique of all kind of nanomaterials, because for the nanomaterials which are very small, we also need the objects of that small size to study their mechanical and electrical properties. Characteristic of various microscope, if we will see, then among the microscope we have certainly not discussed optical microscope, but we have discussed SEM, scanning electron microscope, which has a resolution of in the range of 0.5 nanometer. On the other hand, TEM, which we have not discussed in this course, that is transmission electron microscope, that has a resolution 0.1 nanometer. So, that resolution 0.1 nanometer means if the two objects are placed as close as 0.1 nanometer distant away from each other, we can see those two objects as a different object distinctly. That is what the resolution of 0.1 nanometer. On the other hand, helium ion microscope, we discussed helium ion microscope resolution is 0.35 nanometer, better than scanning electron microscope, no doubt. And then in our scanning probe microscopy, you will see the resolution can be as good as TEM or better than TEM, 0.1 nanometer. 0.1 nanometer means 1 angstrom. We can get the information at the sub nanometer level. If we look at their uses in the history, optical microscope more than 200 years, and the scanning electron microscope age is approximately 80 years, TEM more than 90 years, helium ion microscopy is quite new in the history, which is 15 years old, and scanning probe microscopy is 40 years old. And measurement duration, it is also important that it is not only the resolution that is more important, there are many other factors also important. Measurement, optical is certainly very fast, SEM is also very fast, TEM fast, but also needs sample preparation, SEM also needs sample preparation. Helium ion microscope can also be done very quickly, but scanning probe microscopy is a very slow technique, very slowly, because it is a mechanical movement of the tip, it cannot be very fast, it is quite slow process to get the information, and moreover we cannot get information from a large area. When we see in the scanning probe microscopy, we will see very small area, we will scan atom by atom, and getting the information at the atomic scale, and that cannot be done very fast. Information, in the optical microscope we can get both surface and inside information of the material. SEM only surface, that is why 3-dimensional image. TEM again do not give 3-dimensional image, it is again inside, it can give inside the specimen, because electron beam transmit through the sample, giving the information inside, not the surface information. Helium ion microscope, again it is a scanning microscope, that is why it gives only surface, 3-dimensional image. And SPM, similarly, as we are scanning on the surface, it gives only the surface information, giving 3-dimensional image information, not the inside information. Application, optical microscope is used everywhere, and all these other advanced microscopy technique is used in the science technology and in the invention and discovery of the new materials and understanding the materials properties. Major advantage of scanning probe microscope. Here the resolution of the scanning probe microscope is not limited by diffraction, because there is no diffraction here, because electrons ions diffract, but here probe is touching, there is no diffraction. But what is more important here, the size of the probe sample interaction, how small tip is. If it is atomically sharp, then we get atomically information. If the tip is bigger, then we get similar bigger area information, which can be small as in the picometer range. The accurate height and depth measurement in the Armstrong level. In previous cases, neither scanning electron microscope nor helium ion microscope give us thickness or height quantitatively, but only here scanning probe microscopy give us thickness of the monoatomic layer, diatomic layer at the Armstrong level, and certainly resolution at the lateral resolution also at the atomic scale, provide 3D surface maps, and here certainly again no vacuum is needed, can be operated under ambient condition, allowed to examine surface submerged in liquid. In previous cases, both scanning electron microscope, TEM or helium ion microscope, none of them provides information of the liquid sample, they all do solid sample, because we need high vacuum. But in this case, we can examine the surface submerged into the liquid, that means all kind of biomaterial or biological sample living materials can be studied by using this technique at the atomic scale. The probe sample interaction can be used to modify the sample. We can do the modification of the sample and create structure, and we can do nanolithography. We can go and make one atom sit on a place, another atom sit on another place. We have a nanowires, we can make the nanowires to turn by using the probe tip. We can go and touch to the nanowires and make it to, we can bend it, tune it, turn it. This kind of manipulation can be done by scanning probe microscopic technique. And there are certainly some disadvantages. All technique have certain advantages, certain disadvantages. One of the major disadvantages is that it is a slow process that we have discussed, practically not feasible on a large area. The tip shape is very crucial. If tip shape is not atomically sharp, then we will not get information of that level. Operating platform should be very stable. Very stable means it should not vibrate even at the angstrom level, otherwise the signals will not be very accurate. So, operating platforms has to be highly stable to get the information of the specimen, and also surface should not be very rough. If the surface is very rough, again that is not suitable for this kind to be studied under scanning probe microscopy. Because we are it requires a large quantity of data to make it representative, because we are going to study very small area. To know the information about whole big sample, we need to do a measurement at several places to get an overall idea about the material, rather than just going at few nanometer level investigation or examination. Images are produced in grayscale, certainly SPM, helium ion microscope both also give grayscale, unlike the optical microscope. And we have many different type of scanning probe microscopy, that is scanning tunneling microscopy, abbreviated as STM, that we will go and discuss first. Then we have atomic force microscopy, extensively used to measure the thickness, roughness of the specimen. Magnetic force microscopy, studied for magnetic sample measurements. Chemical force microscopy, electrostatic force microscopy, force modulation microscopy, scanning voltage microscopy. There are many such microscopic techniques available, all are under scanning probe microscope. We will discuss some of those in this course, not the all, but we will begin first with scanning tunneling microscope, in the next lecture. So, in conclusion, what we have seen that in this introduction lecture of scanning probe microscopy, scanning probe microscope provides ultimate resolution down to 0.1 nanometer laterally, horizontally, 0.1 nanometer, unlike the SCM 0.5 nanometer, helium ion microscope 0.35 and 0.01 nanometer vertically. That means 0.1 angstrom vertically means depth resolution, height. Both scanning electron microscope, helium ion microscope, etc., they do not provide height resolution, including the transmission electron microscope, optical microscope, they do not give thickness of the sample quantitatively. But this technique, scanning probe techniques, provides us the vertical resolution or depth resolution with a not only provide the depth or thickness quantitatively, but also to a resolution which is unmatched to any other technique. And it is used routinely to see the atoms, their arrangements and thickness of the monolayer, bilayer, etc. No vacuum requirement and design is extremely simple. Resolution is not limited by diffraction. The tip diameter plays the important role to the resolution. Probe can be used to modify right at the atomic scale on the surface, and spectroscopic technique is very common using scanning probe microscopy. We will see some of this spectroscopic technique used in the scanning probe along with scanning probe microscopy. And these are the reference books. You may find more information. Thank you.